So let's begin this video with another example of taking derivatives of vector-valued functions. Let's find the parametric equations for the line tangent to the curve described by this vector-valued function at the point 1, 0, 0 in R3. Now, as we've seen in an earlier video, this type of parametric equations describe the shape of a helix in R3. So here's my answer. To find a line in R3, I need two things. I need a point on the line, which I have here, and I need a vector that's parallel to the line. That parallel vector is given by the derivative of this vector-valued function. So here's the derivative of my vector-valued function. The derivative is negative sine t cosine t 2. What value of t am I interested in? Well, I want the value of t that gives me the point 1, 0, 0 when I plug it into the original vector-valued function. Looking at the third component, I want the third component to be 0. So that happens when t is 0. So at t equals 0, my derivative, so r prime at 0, is the vector 0, 1, 2. So this is my vector that's tangent to the original curve at the point 1, 0, 0. This is my vector that I'm going to use that's parallel to my line. So my line is described by the parametric equations x, y, and z. So x is going to be 1 plus 0t, y is going to be 0 plus 1t, and z will be 0 plus 2t. Here t could be any real number. So this is the parametric equations for a line in R3. If you want a vector-valued function describing the line, I could write down the vector-valued function 1t, 2t. Okay. Now in Calculus 1, you learned how to take derivatives, and then after that you learned rules for derivatives, such as the product rule. Here we're taking derivatives of vector-valued functions, and there's still a product rule. Actually, there are two. The first is the dot product rule. So I have two vector-valued functions, let's say, r and s. Since the output of my vector-valued functions are vectors, I could take the dot product. If I take the dot product of two vectors, I don't get a vector anymore. I get a scalar. So the dot product of these two vector-valued functions will not be a vector function. It'll be a scalar function. I could take the derivative of that function just like I would in Calculus 1. If I do the derivative of a dot product, I can simplify using the dot product rule, which says that this is equal to what you might expect. The product rule still holds even though I'm taking a dot product. But since we're dealing with vectors, there's a second product, the cross product. The cross product rule is as follows. I have two vector-valued functions r and s. I could take their cross product, and if I do so, I get a new vector-valued function because the cross product of two vectors is, again, a vector. So if I take the derivative of this cross product, then I find the same kind of product rule. So the product rule holds for the dot product and the cross product in the same way. Let's do an example to finish this video of the product rule. So here's an example. Let's say r of t is the vector. What if we use this vector valued function, 1t, 2t, and let's say s is my vector valued function. How about we go with e to the t, 1t. Okay, then the dot product, r dot s, would be not a vector, but a regular scalar function given by e to the t plus t plus 2t squared. So we see the derivative, r dot s derivative, is e to the t plus 1 plus 4t. On the other hand, what would happen if I did this calculation, r prime? So r prime, the derivative of my vector valued function, is 0, 1, 2. And I dot that with s. Then I'll take my original function r, and I'll dot it with the derivative of s. I'm obeying the product rule here and verifying I'll get the same answer I did previously. So if I take the derivative of s, I get e to the t 0, 1. Let's see if the calculation works. So I get 0 e to the t plus 1 plus 2t. So I did this to get 1 plus 2t. And then I will do r dot the derivative of s to give me e to the t plus 0 plus 2t. And you can see that these are indeed the same. Verifying in this example that the dot product rule holds. You could do a similar calculation for the cross product. So maybe I'll do part of it. What would r cross s be? Well, to do the cross product calculation, you form this 3 by 3 array. You put I, j, k up here. The vector r goes in the middle row, so in this case 1, t, 2t, and you put the vector s in the bottom row. So here I go. Then I take the cross product. The first component of the cross product would be t squared minus 2t. The next component would be negative t plus 2t e to the t. What I did for the middle component was cross off the middle row, the top row and the middle column, and then I did not forget the extra negative sign involved with the middle component. And then the last component would be 1 minus te to the t. So now that I have this, I kind of regret doing this example because I'm going to have to do a lot of calculations. But if I wanted to, well, maybe it's not so bad. The derivative, r cross s prime, I can find by taking the derivative of each component. So the derivative here would be 2t minus 2. The derivative here would be negative 1. And then the product rule I need to employ. So plus 2e to the t plus 2te to the t. And then the last component would be 0 minus e to the t minus te to the t, again using the product rule, the usual product rule from Calculus 1. Now I'm running out of space here, but maybe it's a good exercise for you to verify that the product rule holds in this example. You could check that instead of calculating the cross product and then the derivative, you could do this calculation instead. I think I'll leave that as an exercise and conclude the video now. In our next video, we'll see arc length with arc length with vector valued functions. Okay, wonderful.